If you know about oil and gas exploration, but you are not familiar with controlled source electromagnetics, or CSEM for short, then this video is right for you. My name is Daniel Baltar. I am a global interpretation advisor with EMGS. And in this video, I'm going to give you a short background on CSEM and then show you through a demo how CSEM impacts prospect evaluation. First, we will do some prospect evaluations based on seismic alone, and then we will add CSEM so you can see how it looks and feels and impacts the evaluation. Let's get right into it. So let's start by looking at the challenge that we're facing. And the challenge is that in the exploration process, which starts with evaluating a certain area, capturing their area, their acreage. Once we have captured their acreage, we acquire more data and we mature the opportunities that we think might exist in that acreage. And if there is some opportunity that we think is worth further investment, then we put some more money into exploration drilling. And the big challenge that we have is that the failure rate, the economic failure rate of this exploration drilling is extremely high. It ranges from 90%. This is data from Exxon, 90% in play test areas, down to 60% in proven play areas. So this is a very, very high failure rate, from 90 to 60%. And this is due to the uncertainties present in these evaluations that we are producing. And these uncertainties can be very quickly summarized in our assessment of whether there is a hydrocarbon accumulation. So the presence of a hydrocarbon accumulation is challenging to predict. And the size, if there is a hydrocarbon accumulation, the size of the hydrocarbon accumulation is also very difficult to predict. So let's look at CSEM. CSEM is a technology where we lay number of receivers, which are nothing but voltmeters, on the seabed. And we tow an antenna that induces a current into the sediment. And the result of that current propagating through the sediment is measured in the voltmeters. The antenna is typically towed at a certain height over the seabed, though in very shallow waters it might be towed hanging from buoys in the surface. But in general, it's just towed fairly close to the seabed in order to improve the coupling between the antenna and the sediment. With the information recovered by the receivers, the resistivity in the subsurface can be reconstructed. How? We will look at that in more detail later. Now, the key with resistivity is that resistivity, in a sedimentary basin at least, is an indicator of essentially just one thing, which is the amount of water present in the sediment. So water is the only low resistivity thing that goes into the sediment in enough amounts to be measured. So areas with low resistivity mean there is quite a lot of water in the sediment because water is conductive. Areas with high resistivity, that means there is less water in the sediment. And of course, if we are looking for a hydrocarbon accumulation, that means we are looking for a highly resistive body because there is little water left in the sediment. So a hydrocarbon accumulation is, for the CSEM method, just a buried resistive body that we're trying to detect. So a key point is to understand what's the CSEM, so what's the ability of CSEM to detect a buried resistive body. And this is a function of basically just a couple of parameters. First one is the area of the resistive body, and the other one is the net thickness, the product of the net thickness times resistivity contrast of that resistive body. Here you have a traffic light color scheme where red means very low sensitivity or very low signal to noise ratio, and green means very high signal to noise ratio. And green typically means it's very easy to detect. Of course, what you see here is that bodies that are low in terms of area or low in terms of thickness resistivity product are very difficult to detect because the presence of such a body is essentially just noise. When the bodies are much larger in terms of area and thickness resistivity contrast, they are much easier to detect because they produce an easy to measure signal. Of course, the detectability depends also on the depth, and for objects that are buried deeper, you need objects that are larger. So this yellow band that marks the edge of the detection limit is going to the upper right for deeper targets and to the lower left for shallower targets. It's important to note that the CSEM detection ability is very sensitive to volumes because, as you saw before, one of the main reasons of exploration failure is our poor ability to predict size and predict volume of accumulation. Well, CSEM is extremely sensitive, or the main sensitivity of CSEM is driven by the size of the hydrocarbon accumulation. So that's an important factor, as you will see. As for the imaging, CSEM imaging is always done through inversion, and the current state of the art is Gauss-Newton inversion with a TTI physics approximation. So that means we're reconstructing the resistivity parallel and normal to the sediment, as well as the dip and azimuth angles of the resistivity tensor. This inversion is independent of any other type of information, so it can be done independently, and the type of results that it's providing these days are the ones that you can see on the right, which is a blind test where we're trying to predict with CSEM the resistivity of a well log. And the orange line is the first guess at the resistivity, that's the start model. The green line is the CSEM inversion result, so that's the resistivity the inversion is guessing, and the blue line is the average well log. So you can see they match pretty nicely. You have to take into account that they are not expected to match perfectly, basically because the well is disturbing the environment quite a lot. So you are flowing drilling fluids and changing the temperature in the borehole and cracking things up, so you wouldn't expect them to match perfectly. Still, there is a very nice match there within 0.1, 0.2 ohm meter difference, which is quite remarkable. This is the general area of the demo that we want to show you in this video. This is the southern part of the Norwegian sector of the North Sea. The dots in the screen represent the exploration wells, and the area of interest is around this ellipse here. So you can see this area is not as intensely explored as the central part of the North Sea. The color in the dots represents the target interval, and you can see in this area of interest, the target interval sits at around 500 to 600 meters TVD subsea. The datasets available are these seismic line. In these green lines represent the 3D seismic coverage and inline and cross-line numbers. There is also a CSEM survey. Receivers are these black squares, and there is full 3D CSEM coverage in the blue shaded area, and there is partial 3D CSEM coverage in the yellow area. There is an impact of this partial versus full 3D CSEM coverage in the EM imaging, as you will see later. There is a well here in the central eastern part of the seismic survey. These are the structures we're going to be looking into. You can see they are anticlines produced by salt dome development underneath. There are crystal collapse in some of them. So you can see these positive reliefs with crystal collapses, and you can observe that in the seismic it's very easy to see they contain bright spots in them with low velocities and a good positive fluid contact, or what looks like a positive fluid contact in them. You can observe also that there is energy absorption and a multiple pattern and sagging underneath these bodies. So seismically speaking, they are very nice. They are very nice looking prospects. The reservoir dips, as we saw from the well tops, towards the west. It gets shallower towards the east. There is a well here that's projected, so it didn't quite touch this seismic anomaly, but we're going to be looking at the reservoir in a bit more detail now. So these are the logs. You can see a very nice reservoir, about 120 meters of gross reservoir with somewhere around 50, 60, 70% maybe net to gross. This is very low resistivity reservoir because it contains a lot of water, and it's very high porosity reservoir. It's low compaction. So you can see here it reads around 0.6 ohm meters, which is extremely low resistivity. The main risk of these targets, of this play, will be, of course, the seal. It's questionable whether these fairly shallow targets can contain the hydrocarbons in them. So seal is the main risk, and a secondary risk will be whether these are flowable. There is questionable permeability in these bodies, of course. Though in the Netherlands there are similar targets that are producing, and the production rates are quite nice. So in this area, the production rates have never been tested, and it's an unproven play as far as we can tell. The closest discovery is probably 200 kilometers away. In terms of CSEM sensitivity, of course, these targets are extremely high sensitivity because they're fairly shallow. And here what we've done is we have produced a model, a background model like this, and then we introduce a pizza box shaped target, and then we calculate the sensitivity of CSEM to that target with a certain, of course, area and a certain thickness resistivity product. And you can see here on the right that anything above, let's say, 1 square kilometer or even less can be detected as long as it contains some resistivity to it. So sensitivity wise, it's extremely high. Though you don't really need this extremely high sensitivity to have a good CSEM project, but in this case sensitivity is really, really high. So here is a map with the top reservoir horizon that ranges from about 450 meters in the yellow here towards the east to about 750 meters, 700 meters here in the blue on the west. The prospect names that we are going to be using, we have 6 prospects. One is in the lower left here that we are going to call the Western Prospect. The second one up here we're going to call the Northwestern Prospect. The next one around here in the center we're going to call the Central West Prospect, and down here the Central East Prospect. This one up here, the Northeastern Prospect, and this one down here, the Eastern Prospect. Now in this top reservoir horizon you have the imprint. I have converted it to depth using a very simple velocity model, so you are going to see that some shallow velocity effects are leaking into the top reservoir. There are some high velocities in the very shallow subsurface due to incision and fill with high velocity material. The most prominent one is this channel, this sinuous channel that goes from the southwest to the northeast. This is actually not sitting at the reservoir level, it sits in a much younger section, but because I've not corrected for the velocity of that, you can see the imprint of that shallow channel into the reservoir top. There are several other places that we're going to see when we look at the sections. It becomes very obvious that there are incisions that are filled with high velocity material. So let me show you a sum of negative amplitudes around that interval. So you can see that in terms of the seismic response, it's actually very, very compelling. Here you can see that all these highs contain a nice negative amplitude response. This is what you're seeing is a window, the sum of negative amplitudes below the reservoir top. So you can see that a lot of these match structure very, very nicely. These contours are every 5 meters. There's a lot of detail there, but you can still see a lot of these amplitudes actually follow contours to a very high degree. So that's actually very good news. All of them except for the Northwestern Prospect, but as I was saying, this is affected by a high velocity shallow feature that goes across the north of it. So it is difficult to judge whether it fits structure. It definitely more or less fits structure down on the southern edge where you don't actually have a shallow high velocity feature. So let's start looking at these prospects, and let's start on the Western Prospect down here. Okay, so this is the cross line across that prospect. You can see there is an anticline developing here. It's a salt dome developing, and there are some faults going across the anticline. It's forming an anticline on top, and there are faults crossing that anticline, the crest of the anticline. Those faults almost reach the seabed. I don't think they quite reach, but they almost reach. You can observe here some of these very shallow features, these incisions that have been filled with high velocity stuff in some places, and that then create pulled up features. The target would be these obvious seismic amplitudes here in the anticline. The top of the reservoir I have interpreted, because the amount of logs that we have in the area is limited, that it's these this black, which is an increase in acoustic impedance horizon. And as you can see, as you go into the reservoir, into the higher part of the reservoir, as you go up, it changes character to a strong negative or white reflection. So that is, to me, the reservoir top, and that's where I have mapped it. You can see an overall increase in negative reflectivity inside that target, and a very clear positive fluid contact here, which would be a gas or oil water contact. In this case, there is a fairly strong faulting, and most of the other prospects don't quite have as much faulting as this one. What we will do is we will acknowledge that these faults probably represent for this prospect an increased risk of seal, which is obviously the main risk for all of these prospects, which are fairly shallow. This is about 500 TVD subsea, so that means about 400 meters burial. Underneath the target interval, there is a clear frequency impact and absorption and poor image due to the presence of the gas accumulation or the potential gas accumulation here on top. Let's look at another one of these. Let's go to the map of some of negative amplitudes below the top reservoir. Let's look at this from above. And let's look at this prospect here, which we've called Northwest Prospect. Very much the same picture as before. A anticline developing due to a salt dome underneath. There's not much faulting at all on this structure. It's not as pointy as the previous one. This thing that you see up here is the shallow fill with high velocity, which actually deforms the whole anticline underneath the image, and that's why you can't quite check the fit to structure of the amplitudes on this case. But again, very much the same response. This is the reservoir top in black, switches to a negative reflection where the pay zone would be, and then a nice contact is observed, appears here underneath the reservoir in black. So again, an increase in acoustic impedance is the contact. Obvious absorption and shadow underneath the reservoir. Let's go to the next one, which would be this Central North Prospect. This is the largest one in terms of both its area and it contains quite a good thickness. You can see the structure again here, salt dome developing. There is a bit of crustal collapses here, but very much the same picture. The shallow subsurface here is actually cleaner than in the others, so we're a bit more certain about the fit to structure of the amplitudes. But again, very nice contact with an increase in acoustic impedance in black, and the top reservoir horizon goes from an increase in acoustic impedance here in black, it switches to a decrease in acoustic impedance around the top of the reservoir, and a very nice seismic response. There is almost no faulting associated to this prospect, the Central North Prospect, or the previous prospect, the Northwestern Prospect. Let's keep on going. The Northeastern Prospect, you can see here you have a bit of impact from a shallow channel, and there is a small fault running across here. But let me show you how a crossline would look like. There we are. This is the Northeastern Prospect. You can see the start of the Central South Prospect there. But here is the Northeastern Prospect. Again, similar signature. There is a high underneath, a good fluid contact image with an increase in acoustic impedance, a reservoir top that flips polarity as you move into the hydrocarbon filled part of the reservoir, or the would-be hydrocarbon filled part of the reservoir. And in this central part you have the impact of these very shallow, high velocity channel fill that is deforming, it's bringing the structure up. Now you can see one of the faults going across here, it doesn't quite reach the seabed, or it's not as big as the fault in the Western Prospect. This is one of the other prospects with a fault. As you can observe here, as you go towards the east, the burial depth is now shallower. Here we are at around 350 meters maybe reservoir top, which would mean around 250 meters burial depth, which is very, very shallow. So your seal risk would increase towards the east, as we were mentioning before. Let's look at the easternmost prospect. Out here, you can see again very nice fit to structure of those seismic amplitudes. Again, a very similar picture, salt developing underneath. Here you can see, I think, more clearly there is a bit of a crestal collapse in the center of the structure. It looks like that because again you have quite a lot of absorption and image distortion underneath this low velocity feature. A very clear contact image as an increase in acoustic impedance in black here, and the reservoir top, that's this black increase in acoustic impedance outside of the structure or below the contact. And as you move into the reservoir, you can see an increase in the negative reflectivity, and there is a switch. This increase in acoustic impedance completely disappears and it moves to a decrease in acoustic impedance around the center of the target. In this case, you don't really have a lot of faults or major faulting. There are some faults, really minor, that might be affecting the reservoir, but there are these what looks like small gas flags between the top reservoir and the seabed, which would suggest that there is a bit of an increase in seal risk for this prospect compared to the others, because there seems to be some scape features. Now on to the last again, very similar structure being developed underneath, creating a positive relief and clear absorption and shadow underneath the rest of the charged part of the reservoir. A clear contact, that's an increase in acoustic impedance, and a reservoir top that flips polarity. The positive reflection disappears and turns into a negative reflection where the hydrocarbon charge would be happening. You can see this is the smallest one, and there is again a fault, in this case a minor fault going through it. Doesn't really quite reach the sea, but you can see this very continuous reflection right on top, and it's not affected at all by this faulting. So these are all the prospects and how they look. So as a summary of our seismic observations so far, what we have here is 6 prospects, very similar in terms of their reservoir, their structure, their source rock and their seismic response. They're all very, very similar. The main risk of this play is the seal working, and in that sense the prospects in the center. So these 3 prospects in the center will have slightly lower seal risk, so they will be a bit higher up in our chance of success, basically because the prospects to the east are very shallow, and that means these are too shallow. These 2 are very shallow, so that means there is an increased risk of seal breach because of the lack of overburden. And the western prospect here, or I would personally increase the seal risk a bit because of the amount of faulting going through that prospect. If you were to drill this, your favorite prospect would be the one numbered as 1 here, essentially because of its larger volume. It is by far the biggest one. It would be the highest probability and the largest volume, so that would be your favorite prospect around here. So let's look now at what EM would be able to tell us about these prospects. So let's look at the sensitivity of CSEM, and what we do here is we have created basically a 1D model of the Earth. That's approximately more or less what we think the resistivities in this area should look like. And then we introduce in this 1D model of the Earth, we introduce a 3D target at this depth, and I have introduced it at about 500 meters TVD subsea. So what you see on the right is the magnitude of the electromagnetic signal produced by the introduction of a resistive body of a certain area and a certain magnitude in terms of its thickness resistivity. And what you have here is extremely high CSEM sensitivity, of course. You can see that around 1 square kilometer or less, as long as your thickness resistivity product is above maybe 300 or 400 ohm meters squared, which would mean, let's say, a 10-meter reservoir with 20 ohm meter contrast. That would be easily detectable by CSEM. So we are going to see an awful lot of detail on these reservoirs. That's what we know for sure. It's not necessary to have this extremely high sensitivity, but what you will see is that in the EM data, even the smallest of features will actually pop up and we will be able to analyze them, which is actually quite cool. So let's have a look at some QC metrics of the CSEM imaging, and among others, one of the things that you can do is to check how does the control source electromagnetic is predicting the well log measurements. And in this case, what we are comparing is in blue. Here you have the measured log with, of course, a high cut filter applied to it, and in green is the CSEM that the inversion says should be in the sediment in order to explain the CSEM data. You can see a really good match. There is no mixing of these two pieces of information during the inversion. In orange, you have here the resistivity model that the inversion started from, and the green is the final model. So you can see overall a very, very good match, very good prediction of resistivity, except for the deepest part of the well where actually there is salt that the CSEM is starting to see, but the well didn't quite reach. That's why they start to diverge. Pretty good CSEM inversion as far as we can tell comparing to the log. Of course, there's no need for these two to exactly match because they are measuring extremely different frequencies, measuring resistivity at extremely different scales. And of course, the well actually disturbs the environment quite a lot. So you wouldn't expect these two to exactly match, but they in general are very, very similar. They show slight differences in trend. But this is a very good match between those two. So we know the CSEM is imaging the resistivity in the area. So let's start reviewing our CSEM response around what would be my favorite prospect based on seismic, which is this central west prospect out here. And I want to run a seismic line over what I think is more or less the highest point of the structure. You can see here there are some of these high velocity stuff sitting on top, and that's probably going to pop up in my CSEM as high resistivity in the shallow subsurface. So let me overlay the CSEM over this. So there you go, quite an interesting response. There is a very, very small resistive anomaly sitting right at the crest of the structure, but there is hardly any response elsewhere. It looks like there would be something left up here. Let me show you the data range here so that you see what values we have. So this is the color scale that we have here. This magenta is 1 ohm meter, and in red we have about 4 ohm meters. So you can see most of the background values here are around 2.3 ohm meters. Some of these shallow stuff with low porosity, high resistivity features are around maybe 3.5 ohm meters, something like that. In this case, the reservoir is in the middle of a very, very quiet zone, so you can see a very, very weak signal right on top. You will see that how that looks in a map view later on. So let's look at our second favorite prospect, or one of the, let's go back to the west so that we can look at this prospect, the west prospect out here, which was the one that looked good, but that it's pretty faulted. So let's see how that looks in terms of CSEM. So let's overlay our normal resistivity, which is the one that contains the thinly layered stuff. And it's very nice to see here that the response here sits right above where the structure is. There is actually a nice resistor sitting right on top. And if you recall, in this area there is only partial 3D CSEM coverage, and that means there is a bit more of the vertical uncertainty in the placement of the resistor. And what happens here is that it shows up slightly shallower than it should. But when we make a map, you will observe that this is actually sitting right at the crest of the structure. What happens is the resistivity anomaly doesn't quite reach as far out as the seismic does, and that's because it probably has lost quite a lot of pressure due to this faulting, and then there is not as much charge as the seismic would suggest. Let me show you the full picture here. And actually one of the things that you can see in these structures is that the core of the structure, the center part of the structure, is actually very low resistivity often, and that's probably due to the faulting that the anticline develops and the fact that you have salt right underneath. You can see the salt here is actually high resistivity, and the salt probably starts diluting and dilutes into the faulting, and that means it creates essentially paths for the current to flow, and a lot of these anticline cores look actually low resistivity, which is very interesting. But you can see in this case there is a very clear anomaly sitting right on top of the structure, not quite reaching the edge of the structure. And you can also observe here the complex shallow subsurface, where you have actually very highly resistive sediment sitting right underneath the seabed, and they are following, you can see in the seismic there is also a multiple pattern and some pull-up features that indicate that these are high velocity features, so they're high velocity, high resistivity, which would be indicative of actually this being due to low porosity. On the contrary, this structure that we see here is high resistivity but low velocity. The source of that resistivity is actually due to fluid, not to porosity. That the porosity is high, that's why the velocity is low. But what's producing the high resistivity is the lack of brine due to a fluid that's not water being present in the reservoir. Let's keep on looking at our prospects then. So the northwestern prospect is up next. And what you can see here is that this prospect is again slightly lower resistivity, not as much as the one in the western prospect. This northwestern prospect also has slightly lowered resistivity in the core of the anticline. There is a small resistor, not as intense as the one in the western prospect, but there is a small resistor sitting right at the center. And you can observe here this prospect itself is surrounded by high resistivity in the shallower part in the overburden. That is actually the reason why these amplitudes don't quite fit structure. That's because there is so many high velocity features right on top that make it a bit difficult to actually, for these amplitudes to match structure everywhere, because part of this structure is actually pulled up. And you can see again high velocity, high resistivity, which means in the overburden it's porosity. This is high resistivity, low velocity, which means it's fluid driven. It's fluid sourced. Let's look at this, maybe the central east. Let's overlay our CSEM on top. There you go. Very nice image. You can see again the overburden. This high velocity channel out here has a very clear high resistivity anomaly. The same goes with this. But in this case, in the prospect itself, there is no CSEM response at all. Again, the core of the anticline is actually low resistivity, and there is no response whatsoever at the prospect level. At the target level, there is absolutely nothing. It's very, very flat. It's essentially just background. Let's look at the following one. This is our northeast prospect. If you remember, we were moving now towards the east. That means the burial is getting shallower and shallower, which would mean this is higher seal risk, and the seal is less likely here to be working. But actually in this one there is a resistor, even though it's being mixed with the resistor on top. Let me shift around. This actually gets a bit larger as you move out here. So you can here separate the shallower resistor. We go again from the east. So again, the core of the anticline is low resistivity. And here you can see A very clear resistor sitting right at the center of the prospect, and then another one sitting a bit above and to the north, and that's due to the high velocity fill. But there is a very clear resistor on this one, and it's actually stronger than the others. There is a much higher chance that this will be actually charged. Now let's look at the last one. This is our eastern prospect, and let's bring the CSEM on, so the same applies as before. High risk due to seal. But actually on this one, you see the largest resistor by far of this area. Again, the same structure. Low resistivity cord anticline underneath, and the very high resistivity, a very strong resistor sitting right on top of the reservoir. As you can see, compared to the western prospect, where the resistor sat slightly above or right above the reservoir due to the partial 3D CSEM coverage. Here the resistor and this resistivity is completely independent from the seismic, so the fact that your resistor sits right on top of where the reservoir is sourced by the same geological features. But you can see a very, very nice resistor there sitting right on top. So let's compare how an average, what we would do in general would be to take the top reservoir and actually make a window average of the resistivity, where we try to encompass these whole resistors. These resistors, we try to get them into the window average so that we have a good picture of the aerial distribution of the resistivity along this horizon, or so along the reservoir. So here I've calculated, it's a resistivity with a window 100 meters above the reservoir and 200 meters below, so that it sort of encompasses the resistivity. So let me show you. So what you have here, as I was saying, is the resistivity distribution along the reservoir interval, and you can see it is actually quite interesting. First of all, there is a bit of variation, of lateral variation. There is lower resistivity around the reservoir interval towards the east, and it gets higher towards the west, which is natural because the reservoir is actually less compacted. It's deepening towards the west, and that means there is more compaction probably, and maybe slightly different phases, but definitely there are quite outstanding features here, even though you have leaking from resistivities above and below. So part of the resistivity in here in the northeastern prospect is coming from the shallow channel. There's probably some resistivity coming from it. And there is definitely here in the northwestern prospect, there is some resistivity coming from the shallow features that are very resistive. You can see that in the center of our prospects there are different sized resistive bodies, and that indicates the amount of water missing in each one of these prospects. So let's compare the seismic amplitudes with what information from the seismic amplitudes with information from the CSEM. So these were our seismic amplitudes, and you can see they match structure nicely. And let's see how these compare to the CSEM resistivity distribution. If you recall, this was our favorite prospect. Let's see how these compare to an area distribution of EM. So what you can see here is that the CSEM paints an extremely different picture. These prospects in the center, which looked quite okay in terms of risk, they actually contain the smaller columns, particularly the center prospect, which for whatever reason has probably some remaining hydrocarbons at the very, very top. But the amount of water present there that you can see in the CSEM is basically that there is no change in amounts of water across here, but there is a slightly reduction in the amount of water in the reservoir at the very, very top. In the western prospect, here you can see that the seismic, I've tried to keep the seismic in this white outline. This is where the seismic would indicate the contact is. The contact is much, much shallower according to the CSEM. So that means it has quite a bit of pressure compared to what this basically was at a certain point charged with a much larger column, but it has lost the pressure. You can see the contact from the CSEM point of view is sitting up here. The same goes for this prospect, where the CSEM resistor is much smaller than the seismic outline. Then on this central east prospect, there is no column that we can see on the CSEM. There could be still a super small one. Given the sensitivity of CSEM, it's hardly anything there. Actually, you can see this is the smallest resistor that we see in this area, and this is probably just 1 square kilometer. So this is about 1.1 or 1.2 kilometers, 800 meters long and 800 meters wide. So it is an extremely small resistor. So whatever sits in this one, in the central east prospect, is actually smaller than this, because we know we can see this one. So whatever sits in here is very, very small. And if we go towards the east, we can see our two biggest resistors actually sit in the shallowest prospects, which is strange, but it is what it is. And you can see that this northeastern prospect has lost a bit of pressure compared to what the seismic would indicate. So there is a bit of a gap between the seismic indication of charge and the CSEM indication of charge, but still it's bigger than any of the others towards the west. And the largest one is this east prospect, where the resistor actually fills up most of the structure. So it's indicating that contact sits actually very close to where the seismic contact is actually sitting. So your biggest volumes actually sit on this one. So there are really strong implications here in terms of probability of success and drilling sequence. If you had started drilling this one in the center, you would have probably drilled a dry hole. You would have encountered reservoir and high porosity reservoir, but no hydrocarbons. So you would have concluded probably that none of these are working. You would have probably drilled this a bit down deep to prove some volumes, and you would have concluded that this is a very, very risky play. While the truth is, it's not such a risky play, but it's very difficult to judge the volumes based on the seismic alone. The volumes actually seem to be all over the place compared to the seismic. Most of the time you have smaller columns, though on occasion you can have the full column almost being present, like in this eastern prospect. It would just be very, very difficult to figure that out from seismic alone. So if you were to evaluate a drilling sequence here and evaluate display now based on seismic plus CSEM, you would conclude that your probability of success is higher, much higher than you would have guessed from seismic. These are 5 out of 6 are working in terms of containing some hydrocarbons, but your first choice for drilling, your biggest choice would be to drill this one here. It's quite remarkable, in my opinion, that this would be, it would be a very, very different drilling sequence than you would have got from your seismic alone. The inclusion of CSEM in the evaluation makes a great difference. None of these has been drilled yet, but up to now, where we have seen these sort of targets, where you have really, really nice seismic indications and CSEM is also good. What we see is actually that CSEM is always better than seismic at indicating where fluid contacts are, because essentially what you're seeing is the absence of water in the sediment. This is it. Please let us know in the comments if you like the video, or if you have any questions regarding some of the points we've made, or the techniques we have used, maybe the interpretation or the imaging. We would be really happy to answer those. Thank you very much for watching. See you next time.